In this video, we are going to learn how to find the flux of a vector field across a curve. So we've already learned how to take the flux across a surface, but we can extend this idea to find the flux across a curve. So how do we do this? I'm going to draw a couple of pictures. So I'm going to draw my x and y axes. So my x-axis and my y-axis. And I'm going to copy this. I'm going to draw two pictures. So I'll draw two curves here. So I will draw two curves. And in the first picture, let me draw the curve, maybe something like this. And I'll call my curve C. And I'll draw an arrow for the direction of motion. Let's say it goes that way. And in the second picture, let's say that I have a closed curve, which means it'll start and end at the same point. Okay, and I'll call my curve C. And again, I'll draw arrows for the direction of motion. So when I have a curve like this, our normal vector, I'm going to let n hat be my unit vector that's normal, which means perpendicular or orthogonal to the curve. There's two choices for how I could draw that, because I could draw a vector that's perpendicular this way, or I can draw it in the exact opposite direction. So the convention is that as we travel along the curve, choose the normal vector that points to the right. Points to the right. So as I'm moving along the curve, I need my normal vector to point to the right, which would be this way. So if I take like an arbitrary point here, and then I draw a normal vector pointing to the right as I travel along the curve, something like this, I'll label that n hat. And that's perpendicular. It's normal to the curve. Let me draw one other one. Maybe at this point, again, as I'm traveling along the curve, if I draw that normal vector pointing to the right, that would be this way. So my normal vector, and then perpendicular. Okay, and along my closed curve, if I pick a couple points and draw the normal vectors, maybe at this point my normal vector would point this way, right? That would be to the right as I'm traveling along it. And maybe somewhere over here, if I draw the normal vector, that would be pointing that way. Some way like this. My normal vector, perpendicular to the curve. So when I have a closed curve, notice that these normal vectors point outward. So if we're trying to find the flux across a closed curve, it means we are finding the outward flux. The outward flux, which will represent, how much of the fluid is crossing this curve outward. So our definition of flux of our vector field through the curve C is we're going to take a line integral over the curve of our flux dotted with that unit normal vector. So it's a very similar formula to what we saw for flux across a surface, but with a surface I had a surface integral. Now that I have a curve, I do a line integral. So how do we interpret this? Conceptually, the flux of our vector field is the integral. It's the integral of this f dotted with the normal vector. That's what's called the normal component of f along the curve. So that measures the extent to which f is going normal to the curve, or I can write that as the extent to which f is going across the curve. So in the same direction as that normal vector. So if I have my vector field f, and this just means I have some formula for the vector field, and if this is a velocity vector field, our flux measures how much fluid passes through the curve in units of area per unit time. So if my curve is like this at an angle, and my normal vector is pointing this way, well, and these blue vectors are the vector field arrows, well, those are generally in the same direction as this normal vector arrow. So there's some flux here. If the curve was exactly like this, where the vector field arrows are perpendicular to that curve and in the same direction as this normal vector, well, there's a lot more flux. There's way more of the fluid that's passing in this direction that is normal to the curve. And then if the curve is like this, parallel to these vector field arrows, well, the normal vector is totally perpendicular to these vector field arrows. And in this picture, there's no fluid that would be passing through this curve. So there's no flux. Okay, so let's do an example. Let's say that I have this vector field f, and C is the part of y equals x squared from the point -1, 1 to the point 2, 4. So it's the part of this parabola, and it's drawn in this picture. And we also have the vector field arrows drawn for this portion of the picture. And I want to find the flux of the vector field through that curve C. All right, so the flux, let's recall the formula for flux. Because it's across the curve, I do a line integral over the curve of my vector field dotted with that unit normal vector, ds. So we're going to need to find this unit normal vector. And if I go to my picture, since we're traveling from this point here to the point here, I'll draw an arrow for the direction. So an arrow for the direction. And let's draw a couple of normal vectors. So if I pick a point here and I draw a unit normal vector, it's got to be pointing to the right as I go along the curve. So that would be this way. So my unit normal vector, so perpendicular to the curve. Let's draw one more spot. Maybe if I draw it here, my unit normal vector, again, it's pointing to the right as I go along the curve. That would be this way. Okay, and well, so how could I get that normal vector? I'm going to notice that one of the things that it's normal to is if I were to draw the unit tangent vector, so, and remember we call that t hat, that those are perpendicular to each other. So to get that unit tangent vector, we need to parameterize the curve. So parameterize the curve. So to parameterize this, I would normally plug in for the x to get y. So I am going to let x be equal to t, my parameter. And if I plug that in, we would get y equals t squared. And then what's my domain? What is my domain for t? Well, because x equals t, and the x values start at -1 and they go until 2, t goes from -1 until 2. So I got my parameterization. So now remember, let's recall that our unit tangent vector, t hat, the formula for it is it's the velocity vector divided by the length of the velocity, the length of the velocity. And the velocity vector, to get that, we take the derivative of each of these components. So I'm going to write that as a vector. So the derivative of x, well, that's derivative of t is just 1. And the derivative of t squared is 2t. On the denominator, I'm going to leave the length as it is, the length of v. Something really nice is going to happen to it later, so I'm going to leave that as it is. Well, okay, so that gives me this unit tangent vector. How do I now get the normal vector based on that? Okay, so based on this, my unit normal vector, there's actually a really nice way to get this. We don't want to change the length at all. This already has the correct length, length 1. So I'm going to leave this constant on the denominator as it is, the length of that velocity vector. And I'm going to change the order of these two terms on top. So I'll put the 2t first and the 1 second. And what I'm going to do is put a negative in front of the 1. And I could check that now if I do the dot product and I multiply these x components together, I'll get 2t. Multiply the y components together and I'll get negative 2t. And then summing them, that's 0. So, and these scalars on the bottom don't affect that I'm getting 0 on the numerator. 0 divided by something is just 0. So with this, t hat divided by n, dotted with n hat is going to be 0. Their dot product is 0, so they're going to be orthogonal. They're going to be normal. That's not the only thing that could work here, because I don't have to put the negative in front of that second component. I could have put it on the 2t. So I could have done that, or we could have done the negative in front of 2t and then done comma 1 over that length of my velocity. But there's a way to know which one it's going to be based on the picture, which is for any normal vector that I have here, they're always pointing downwards, meaning their y component is negative. And that only happens in this one. So only in this one is the y component negative. Y component is negative, which is what I would expect to happen based on the picture. So that lets me rule out the second choice. Now I know my unit normal vector. We're ready to plug into our formula. So this flux, this converts to a regular integral, which based on my interval for t goes from -1 until 2. And I take my vector field, and I'm going to plug in our parameterization. So when I do that, I'll get the vector, so I'll get y first, which is t squared, and then comma negative 2x, which becomes negative 2t. Dot that with the unit normal vector, which is 2t comma negative 1, divided by the length of the velocity. And remember that ds becomes the length of the velocity dt, right? I'll highlight that. ds becomes the length of the velocity dt. And this is really nice because the length of the velocity on the top and the bottom cancel. Now I just got to do that dot product. So I get the integral from negative 1 to 2. That dot product gives me 2t cubed and then plus 2t dt. From there, I'm going to trust that we can do this antiderivative and we can plug in the 2 and the negative 1. So from here, it's not too bad. I'm just going to write a dot, dot, dot. We would do that antiderivative. We'd plug these numbers in. And if we do that, we are going to get 10.5. And that's our flux. Just doing a reality check, does it make sense that this is positive? Well, if I look at my picture, for this part of the parabola, the normal vectors are pointing generally the opposite direction as the vector field arrows, which are kind of going this way. So I'd actually expect the flux to be negative for this portion of the parabola. But then for this portion of the parabola, the vector field arrows are generally going the same direction as this normal vector. So I'd expect this part to be positive flux. But the vector field arrows get larger and larger the higher up I go. So I expect the flux to get bigger and bigger over here. So I'd expect there to be more positive flux than there's negative flux on this side. So it does make sense to me that this is positive overall for my answer.